Using building steel as a down conductor is a standard practice for lightning protection systems. This is recognized within the UL 96 as standard for lightning protection systems and also NFPA 780, which is the standard for the installation of lightning protection systems. While Section 250.60 prohibits using water pipes, metal building frames, and other non-conductive objects for grounding electrical systems, it does not apply to lightning protection systems. NFPA 780 specifically allows grounding to building steel, but there is a stipulation. The connection needs to be made below grade level. UL certification ensures that the lightning protection system meets the safety and performance requirements set forth in UL 96A. It is understandable to have concerns about using building steel as a down conductor because it may seem to conflict with Section 250.60. However, the specific requirements for lightning protection systems in NFPA 780 take precedence and allow this practice. The Master Lightning Protection Specialist certification also provides assurance that the system has been properly designed and installed to meet the necessary safety standards. In summary, using building steel as a down conductor is an acceptable and common practice for lightning protection systems. It does not violate Section 250.60 and is compliant with NFPA 780 and UL 96 when properly installed and certified. Now let's delve deeper into the specifics of each of these standards and codes to understand why this practice is acceptable and safe. Firstly, let's look at UL 96A. This standard provides the requirements for lightning protection system installation. It covers the materials, components, and design considerations necessary to protect structures from lightning strikes. One key aspect is the use of building steel as a down conductor. The standard recognizes that building steel, when properly interconnected and grounded, can provide an effective path for lightning current to flow to the ground. Secondly, let's explore NFPA 780. This standard provides detailed guidelines for the design, installation, inspection, and maintenance of lightning protection systems. It complements UL 96 and offers more specific requirements for various aspects of the system. NFPA 780 explicitly allows the use of building steel as a down conductor, provided certain conditions are met. These conditions typically include ensuring that the steel is electrically continuous from the roof to the grounding electrode system, and that connections are made with appropriate bonding techniques. Thirdly, let's consider Section 250.60 of the National Electrical Code, or NEC. This section addresses grounding requirements for electrical systems. It generally prohibits using building steel as a grounding electrode for electrical systems. This is because building steel may not provide a reliable or low impedance path for fault current to return to the source. However, it is crucial to understand that Section 250.60 does not apply to lightning protection systems. Lightning protection systems are designed to handle significantly higher currents and voltages than typical electrical systems. Therefore, they have their own specific grounding requirements outlined in NFPA 780. Furthermore, the grounding requirements for lightning protection systems are more stringent than those for electrical systems. This is because lightning strikes can introduce massive amounts of energy into a structure, and the grounding system must be capable of safely dissipating this energy into the earth. Now let's address some common concerns related to the use of building steel as a down conductor. One concern is the potential for corrosion of the steel over time. Corrosion can weaken the steel and reduce its ability to conduct lightning current. To mitigate this risk, it is important to ensure that the steel is properly protected from corrosion with coatings or other protective measures. Another concern is the potential for lightning current to damage sensitive electronic equipment within the building. Lightning current can induce voltage surges in electrical and electronic circuits, which can damage or destroy equipment. To address this concern, surge protective devices, or SPDs, should be installed at the service entrance and at other strategic locations throughout the building. SPD can help to divert lightning current away from sensitive equipment and protect it from damage. Another element to consider is the proper bonding of all metallic components within the building. This includes pipes, ducts, and other metal objects. Bonding helps to create a low impedance path for lightning current to flow to ground, and it reduces the risk of side flashes, which can occur when lightning current jumps from one object to another. When inspecting a lightning protection system that uses building steel as a down conductor, there are several key things to look for. Firstly, verify that the steel is electrically continuous from the roof to the grounding electrode system. This can be done by visually inspecting the connections between steel members and by using a multimeter to measure the resistance between different points. Secondly, check that the connections are made with appropriate bonding techniques. This may involve using CAD-welded connections or other approved methods. Thirdly, ensure that the steel is properly protected from corrosion. Look for signs of rust or other corrosion damage and ensure that any protective coatings are intact. Fourthly, confirm that surge protective devices are installed at the service entrance and other strategic locations throughout the building. Verify that the SBD are properly rated for the expected lightning current levels and that they are functioning correctly. Fifthly, verify that all metallic components within the building are properly bonded together. Check the bonding connections between pipes, ducts, and other metal objects to ensure that they are secure and that they provide a low impedance path for lightning current to flow to ground. Finally, ensure that the grounding electrode system is properly installed and maintained. Check the condition of the ground rods or other grounding electrodes and verify that they are properly connected to the building steel. Let's discuss the importance of UL certification for lightning protection systems. UL certification provides assurance that the system has been tested and evaluated to meet the safety and performance requirements set forth in UL 96A. This certification is important because it demonstrates that the system is designed and installed to provide effective protection against lightning strikes. UL-certified lightning protection systems are typically inspected and audited on a regular basis to ensure that they continue to meet the requirements of the standard. This helps to ensure that the system remains effective over time and that any potential problems are identified and addressed promptly. In summary, using building steel as a down conductor is an acceptable and common practice for lightning protection systems when properly installed and certified. It is important to understand the specific requirements of UL 96A, NFPA 780, and Section 250.60 of the NEC to ensure that the system is compliant with all applicable standards and codes. By following these guidelines, you can help to protect buildings and their occupants from the hazards of lightning strikes. Furthermore, proper maintenance and regular inspections are crucial for ensuring the long-term effectiveness of a lightning protection system. This includes checking the condition of the grounding electrodes, the connections between steel members, and the surge protective devices. Any damage or deterioration should be repaired promptly to maintain the integrity of the system. It is also important to keep accurate records of all inspections and maintenance activities. This documentation can be helpful for tracking the performance of the system over time and for identifying any potential problems. When designing a lightning protection system that uses building steel as a down conductor, it is important to consider the specific characteristics of the building. This includes the height, shape, and construction materials of the building, as well as the occupancy and the types of equipment that are housed within the building. The design should also take into account the local lightning strike frequency and the potential for severe weather events. It is essential to consult with a qualified lightning protection specialist to ensure that the system is properly designed and installed. A qualified specialist will have the knowledge and experience necessary to assess the risks and to develop a system that provides adequate protection for the building and its occupants. Additionally, it's vital to understand the role of equipotential bonding in a comprehensive lightning protection strategy. Equipotential bonding involves connecting all metallic components within a structure to a common ground point. This minimizes voltage differences and prevents dangerous side flashes that can occur during a lightning strike. Effective equipotential bonding is crucial for protecting sensitive electronic equipment and ensuring the safety of occupants. The connections must be robust and designed to handle the high currents associated with lightning events. Bonding conductors should be sized appropriately and installed according to industry standards. Regular inspection of bonding connections is necessary to ensure their integrity over time. Corrosion, loose connections, or physical damage can compromise the effectiveness of the bonding system. Proper bonding techniques such as welding or using listed connectors are essential for creating reliable and long-lasting connections. In addition to bonding, surge protection devices, or SPDs, play a critical role in mitigating the effects of lightning strikes. SPD are designed to divert surge currents away from sensitive electronic equipment, preventing damage or malfunction. SPD should be installed at various points throughout the electrical system, including the service entrance, distribution panels, and individual equipment locations. The selection of SPD should be based on the specific voltage and current requirements of the equipment being protected. SPD are available in a variety of types, including hardwired devices and plug-in modules. Hardwired SPD typically offer higher surge capacity and are more suitable for critical applications. Plug-in SPD are easier to install and are often used for protecting individual pieces of equipment. Regular testing of SPD is necessary to ensure their continued effectiveness. SPD can degrade over time due to repeated surge events. Testing should be performed according to manufacturers' recommendations and industry standards. Replacement of SPD should be performed promptly when they reach the end of their service life. Furthermore, the placement of air terminals on a structure is critical for effective lightning protection. Air terminals, also known as lightning rods, are designed to intercept lightning strikes and provide a safe path for the current to flow to ground. The placement of air terminals should be based on a rolling sphere analysis, which takes into account the height and shape of the structure. Air terminals should be located at the highest points of the structure, as well as along edges and corners. The spacing between air terminals should be determined based on the rolling sphere method. The rolling sphere method involves imagining a sphere rolling over the surface of the structure. Air terminals should be placed in locations where the sphere would touch the structure. This ensures that all points on the structure are within the zone of protection provided by the air terminals. Air terminals should be constructed of corrosion-resistant materials, such as copper or aluminum. They should be securely mounted to the structure and connected to the down conductors. The connections between air terminals and down conductors should be made with appropriate bonding techniques. Regular inspection of air terminals is necessary to ensure their continued effectiveness. Damage, corrosion, or loose connections can compromise the performance of the air terminals. Replacement of air terminals should be performed promptly when they are damaged or corroded. The routing of down conductors is also an important consideration in lightning protection system design. Down conductors provide a path for lightning current to flow from the air terminals to the grounding electrode system. Down conductors should be routed as directly as possible and should avoid sharp bends or loops. The number of down conductors required depends on the size and shape of the structure. Multiple down conductors are typically required for larger structures. Down conductors should be securely attached to the structure and protected from physical damage. The connections between down conductors and the grounding electrode system should be made with appropriate bonding techniques. The grounding electrode system is a critical component of a lightning protection system. The grounding electrode system provides a path for lightning current to dissipate into the earth. The grounding electrode system should be designed to provide a low impedance path to ground. The type and number of grounding electrodes required depends on the soil conditions and the size of the structure. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. Ground rods should be driven deep into the earth and spaced appropriately. Ground plates should be buried in the earth and connected to the down conductors. Concrete encased electrodes should be embedded in the concrete foundation of the structure. The connections between the down conductors and the grounding electrodes should be made with appropriate bonding techniques. Regular inspection of the grounding electrode system is necessary to ensure its continued effectiveness. Corrosion, damage, or loose connections can compromise the performance of the grounding electrode system. Testing of the grounding electrode system should be performed periodically to verify its impedance to ground. This testing should be performed by a qualified lightning protection specialist.